With this module, we are starting a new topic of chemical thermodynamics devoted to multi-component systems. So, what exactly are multi-component systems? They are systems containing multiple components in the sense used in the Gibbs phase rule. Here, a component refers to a chemically independent substance present within the system. From a thermodynamic standpoint, we focus on multi-component systems that are in thermodynamic equilibrium. Thermodynamic concepts describing multi-component systems are broadly relevant. They can be applied to an extremely vast range of disciplines, from microbiology to metallurgy and consumer goods production. Multi-component system consists of one or many mixed phases. Such phases are referred to by various names: gaseous or liquid mixtures of substances, solutions, and even metal alloys, to name a few. A defining characteristic of a mixed phase is its homogeneity. This means that the substances within a mixed phase are uniformly dispersed, down to the molecular level. This distinction sets them apart from heterogeneous mixtures and colloidal systems, such as emulsions and suspensions. A true single phase remains stable due to intermolecular forces binding its constituents together. Such a phase won't segregate and its constituents won't sediment when left undisturbed. Many of the chemical processes and phenomena that surround us involve the mixing of substances. Fortunately, the thermodynamics of such mixtures can be understood by building upon concepts we have already introduced for pure substances. As we move forward into this topic, we will ensure that you are well equipped to grasp its complexities. This figure illustrates phase equilibrium in a multi-component system. There are several key ideas to comprehend. Consider a system in equilibrium at a constant, externally controlled pressure and temperature. Across all phases, the system maintains uniform pressure and temperature, denoted as P and T in our illustration. However, the amount of each substance can differ from one phase to another. The figure demonstrates it for three substances across three phases, A, B, and C. Each amount is denoted with a superscript indicating the phase and a subscript representing the substance. This is a typical nomenclature for physical quantities describing systems with multiple mixed phases. The criterion for equilibrium in such a system is the equality of chemical potentials for a given species across all phases. This is represented by the equations shown here. For example, the chemical potentials of substance 1 in phases A, B, and C are the same, and this holds true for the other substances as well. If this were not the case, substance 1 would transfer between phases until the chemical potentials balanced out. This equality of chemical potentials applies to all substances in the system when true equilibrium is achieved. What changes when chemical reactions are also at play in a multi-component system? When substances are involved in a chemical equilibrium, their chemical potentials become interrelated. From a thermodynamic viewpoint, it doesn't matter in which phase a reaction participant resides, because its chemical potential is the same across all phases. Although reaction rates are influenced by many factors, including the location of the reaction participant, these details are beyond our current thermodynamic focus. When there is a true chemical equilibrium among substances in a particular phase, their chemical potentials are interrelated in every phase. We have already explored the concept of chemical equilibrium in previous discussions. At this moment, our emphasis is on components, which are chemically independent substances. Introducing additional chemical equilibria could simply reduce the number of independent components by creating new interrelationships between them. Our focus is on these components and their chemical potentials and amounts in each phase of the system. As we move forward in our exploration of multi-component system, let's discuss their degrees of freedom. For simplicity, let us consider a system that has only one phase and C components. How many variables in such a system can we adjust without impacting the others? The Gibbs phase rule provides an answer, C plus 1. This is the number of independent variables that define the state of the system. So, which are these independent variables? Primarily, they include pressure, temperature, and C-1 mole fractions of the components. The reason behind considering only C-1 mole fractions is straightforward. The sum of all mole fractions in any mixed phase equals 1. If we know the mole fractions of C-1 components, we can easily determine the last one. On the other hand, we have the freedom to modify the amount of C substances in the phase, in addition to pressure and temperature. Why is there such a discrepancy between these two sets of independent variables? The reason for this is the distinction between extensive properties, such as amounts, and the intensive variables, which are considered to define the system's state according to the Gibbs phase rule. We can express these amounts in terms of the total amount and mole fractions of the system's components. The key takeaway here is that the total amount of substance in a phase is not relevant to its state. Instead, the state of a mixed phase is defined by its relative composition, not by the absolute number of moles of individual substances present.